We ready to continue? Small subtitle, Edge Colorings of Multigraphs. Vizing says that chromatic index is between delta plus 1 and delta for simple graphs. For multigraph, this is not true anymore. For multigraphs, like if we take this, let's say this graph, how many colors we need? 6. All 6 edges must be colored differently, like color 1, 2, 3, 4, 5, 6. And we can go even further. We can take more of these parallel edges, maybe differently, maybe 2 here, 3 here, and 1 here. Or let's say 4 here. How many colors we're gonna need? You see that here every two edges share one end vertex, so every 2 edges must be colored differently. So the number of colors in such a graph, such configuration, is actually the number of edges. And here the number of edges is 2 plus 3 plus 4, it's 9, yes? We need 9 colors, yes? Okay, and these such triangles or whatever, it can be like this, and so on. All these, I call it Shannon triangles. So Shannon triangle officially is like this. Let's say we have here A, B, C edges, so the A plus B plus C colors. We need it, yes. This is the worst graphs, the worst multigraphs. They need most number of colors. Okay? So there are 2 theorems which we will not prove now. Yes, first is the Shannon theorem. Shannon. Okay. Which says about multigraphs, that G's multigraphs here is at most three-half of delta. We should be careful here, delta. At this vertex, U, degree of U is A plus C. Yes? At this vertex, V, degree is A plus B. And at this vertex W, degree is B plus C. Okay? So it's not like 2. We count every edge. It appears 5 times some edge with multiplicity 5. Then we say we count 5. Yes. Okay. This is Shannon theorem, and there is another theorem, Vizing for multigraphs theorem. He's also some Gupta. It must be Indian guy. Yes. Gupta is Indian. Yes. Vizing Gupta, yes. Are you happy? Gupta theorem. Probably they prove it independently, yes. Delta of G. Let me write it nicer. Plus multiplicity of G. Do we know what is multiplicity of G? Multiplicity. Let me define it, okay? First, what is multiplicity of an H? Yes, based on some example. we have a look where we have some edges and count the number of parallel edges. This is a parallel edges. So we have here 2. We have here 1. We have here 2. We have here 3. So what will be the multiplicity? What do you think? The maximum number out of this. So multiplicity of graph G is 3. Maximum number of parallel edges. Number of parallel edges. So if you take the degree, okay, and if we take multiplicity, and we count it together, then we get that's what we want. Yes. So, but even here in degree, we count the multiplicity of a vertex. Like, what will be maximum degree here? Me is 3. Multiplicity is 3. But what is of this graph? What is maximum degree of this graph? 5. Yes. So you should be careful. It's not like 3 yes. Of I don't know. It's just consider it. Okay. So maybe in the exercise part we will see this proof Shannon theorem. Yes. I will give it as an exercise, and this is a little bit too much. Yes. Before we go to Snarks, or maybe we can go now to Snarks. Yes. Okay, let's go with Snarks. Subtitle, second part, Snarks. Snarks, so we study here cubic simple graphs. Snarks are not well defined. It depends what we need for. Yes. So, but usually we want to get rid of some trivial cases. Generally, we say snarks cubic graphs of chromatic index of chromatic index 4. So the cubic graphs which are of class 2. Yes. Okay. So we have here one theorem, lemma, which is called Blanchet lemma. Let's see be a 3H coloring of a cubic graph G. Okay, G is here, cubic graph. We speak now only for cubic graph. And let's see the edge coloring. Oh, sorry, here is a 3. 1, 2, 3. Some 3 edge coloring of a cubic graph, yes. Okay. Now this is small c. Let's big C be an edge cut. We know what is edge cut, yes? Okay, we will explain again. Now, denote by small ci the number of edges of C that are colored by I. Then C1 congruent to C2 congruent C3 modulo So let's illustrate this. This is our C, the edge cut, C. So this is edge cut in the set of edges. When I remove it, I get 2 parts. And this is like left side and right side. Now, since the graph is colored, some of these edges are colored blue, some of these edges are colored pink color, and some of these colored green, let's say. So this is C1, this is C2, and this is the number, yes? And the number of green edges is C3. Blanche lemma claims that these 3 numbers are of the same parity. All are even or all are odd. Has anybody heard of this before? Or this is completely new? Okay. Blanche is Croatian mathematician, and he, okay. Okay. This is color, the blue is color 1, and the pink is color 2, and the green is color 3, okay? So let's take the graph H1, 2. We defined it before, 1, 2. We take the colors 1 and 2. Blue and pink. Because it's cubic graph. What will be this? How? Can you tell me what is this graph? How it looks? Sorry? Cycles. Really? Cycles. Or wavelength. Every component will look like this. Look. Some pink, some blue, some pink, some blue, some pink. Graph is finite. It cannot go like. And at every vertex, we have all 3 colors. If we remove, instead of taking these 2 colors, we can remove the green one. What we're gonna left? Cycles. What the length of these cycles? Even cycles. Exactly. Even cycles. Okay? Okay? Sorry?
Can you repeat this?
What?
Can you repeat this?
From where?
Or is this given cycle?
Why is in cycle? So at every vertex we have all three colors. Okay? So let's say we started this and we go through this pink color. We come to this vertex. We come by pink. We go out by blue. We come by blue here. We go out by pink color. We come. So they are alternating. It's not possible to. If you get odd cycle, you will have blue blue or pink pink. So this is not possible, yes, because it's property rich coloring, yes. Okay. So let's draw these cycles. How this look? We're gonna have something like this, then going like this. Maybe I can back by blue. Then I maybe going here will be like pink. Maybe I cross here. And this is one cycle. And maybe I have another cycle here. Maybe I go here. Maybe we go by pink back. Okay? All possibility you can have it. I just consider these two colors. But you tell me how many edges I have here. Of these two colors together. You know, when I go from left to right, I go back from right to left. I go left, right, back. So the number of edges, even. Number of edges. So that's mean. So what was C1? C1 was the blue and C2 was the pink. So C1 plus C2 is even. Do we agree? If C1 plus C2 is even, what we can say about C1 and C2? Then C1 is congruent C2 mod 2. Okay? In the same way, we showed that C1 is congruent to C3. And then automatically C2 is congruent with C3. So all of them are, that's Ganush's lemma, yes? This is the end of the proof, yes? Okay. Look now this. Listen to me. Let's look this graph. Is this graph cubic? Is this as cubic, yes? Can we color it with three colors? Is this graph is it class 1 or class 2? Try to color it by three colors. You make it? Come to show us. Have to do it here. You get it? No, you can't. We cannot. Why? Why? So what's the problem with it? Yeah. So why this graph is not color? This has chromatic index 4 because however we color it with, let's say, blue. So we have then what was C1? C1 is then ENA 1, and then C2 is 0, and then C3 is 0. By Blanusha, yes? By Blanusha, this is then contradiction because they are not all of the same parity. So you don't have to try to color it. You can just apply Blanusha, yes? So what is the conclusion? If our cubic graph has a bridge, if G is cubic plus has a bridge, then chromatic index is 4. Having a bridge force to have chromatic index. So this is what we consider as a trivial reason. Having bridge, trivial reason that implies chromatics number to be equal to 4. And we don't like that. So for Snarks, so now we change the definition of Snarks. We say, okay, Snarks cubic plus bridgeless graphs of chromatic index 4. So we would like to get rid of this trivial reason why something has chromatic index 4 and then get nice class of graphs and then work with this class of graphs. So first we get rid of bridges. Second thing, okay? Second thing, now we would like to get rid of 2H cuts. We don't like our Snarks to have 2H cuts. It's a kind of, again, trivial reason. And we're going to see why now. So, let's do this proposition. It's all the time G cubic, okay? I don't have to write always. G is cubic here, yes? You can write yourself. G, okay, cubic, and we have, in this cubic graph, we have 2H cut. Okay, and let G1, G2 be the components of G minus now finally let and okay, a lot of assumptions, we're going to draw it less. Then, big then chromatics number of G is 4 if and only if chromatic number of one of these graphs is 4. Maybe I can little bit make it nicer. So, oh yeah, okay. Sorry. I will draw it. I will illustrate now. Look. I will draw it now. It is something like, maybe I use some other color, yes. This is G1, this is G2, and then we have X1, Y1, X2, Y2. Okay? Now I take copy of this. Maybe I first move it here, and then copy, and then paste. I will get 2 graphs now. Okay? I will now remove, no, I will now remove this and this. Okay. Wow. And I will put these edges. And now this is G1 star, G2 star. Now the proposition claim, this has chromatic number 4 if and only if this one has chromatic number 4 or this one has chromatic number 4. Okay? So look, I have 2 edge cut. I can remove 2 edge cut and put this edge x1, x2 to make this graph. Maybe I can explain this. So where is this? Where is this pencil? I don't have it. Click or navigate. Laser, yes. Done. Do I have the laser now? How I make the laser? Zoom. Anybody see the laser? I don't know. I don't see it, I'm blind. Paint text. The laser. No, I want to. Can you reset the default? Do you see the laser now? Oh, okay, okay. I reset to the default. Okay, okay. So look, we have this cubic graph, in which case maybe red, which case 2 edge cut here. Yes, cubic graph with 2 edge cut. So we remove these 2 edge cuts. We get 2 parts, 1 part and 2nd part. But we put this edge to make this graph now cubic, because it has edge here, this vertex and this one, and also this one and this one. When we remove these 2 edges, by this we make this one cubic. By this we make this one cubic graph. This is G1 star, G2 star, okay? Now, from one cubic graph with 2 edge cut, we make 2 smaller one cubic graphs. And property is this has chromatic index 4 if and only one of these two have chromatic index 4. And on this thing, from their perspective, you can say, okay, the reason why this has chromatic number 4 is one of these graphs, maybe both. Okay, we will prove this, but the reasoning is we don't like our snarks to have 2 edge cut. Because if it has 2 edge cut, I will get smaller snark out of this in a very simple way. Removing the 2 edge cut and making this, putting here, one of these will be snark. This is the in a similar way reasoning with the one, with the bridge. We don't want to have some simple reason why it is not 3H colorable, and here this simple reason is it contains something smaller that has. So after this proposition, we will change our definition of snark by saying snarks by
X1 may be adjacent to X2 already. So
sorry.
What if in the original graph X1 is adjacent to X2? So we make an additional edge or
if we have H here. Yeah, but then you have another H here, and another 2 H cut, yes. Doesn't matter, yes. Sorry?
G1 star. G1.
Yeah. Yeah, but we also say we don't have. Yeah, we can say it's multi-graph. We can also use multiple edges. We can say also this. So we don't. Here the story is we don't want to have 2 edge cuts. We also want to say we don't want to have 2 signals, 3 signals, 4 signals. So in our definition of snark, we don't want to have 2 cycles. Cycle of length 2, that's multigraph, okay? We don't want to have this, yes? Because if I have this in my graph G, I will make I will remove this and I will make directly connect A and B, yes? And now, if this is a snark, not index 4, this will be also index 4. Because if this is not index 4, I color this, let's say, with color 1, then I put here color 1, color 2, color 3, and I color it. Okay? So, it can be edged, no problem. But in this way, we reduce it. If I get parallels, I will reduce it. Okay? So, point is to get rid of these small things like 3 cycle, 4 cycle, parallel edges, bridges, and so on. Our snark to be nicer one. Not to have some of these small things, yes. Okay? This is the idea. We are not going to reduce everything because we don't have time, yes? But after this, so why this is true? So I'm going to prove this, okay? I'm going to prove this theorem, okay? Proposition, let's go back to the proposition. You have some more questions? You have some more questions? Or it's okay? Do you have questions?
Actually, in this we are having some doubt, like if X1 X2 is already adjacent. If X1 X2 is already adjacent in the graph.
X1, X2. If it is also in the graph, okay?
It is already adjacent. Okay. If we make another edge, then it will be multi-graph.
It will be multi-graph.
But if we are not creating that edge, that will not be cubic, right?
You are adding the sequence cube. You're going to have here the old one. You're going to have here old one edge. It will be like that.
It will be cubic.
Yeah, it's okay. Let's have also multigraph if you want. But I'm saying, as soon as I get parallel edges, I'm gonna get this way to this. You can say you can get loop, okay, but I will have bridge. I can also maybe with this operation get this, but then this is bridge. Then I say, oh, I don't want bridges. I don't want two loops. I don't want multiple edges. I don't like two edge cuts. No, I'm just removing the things, yes, reducing. So let's go. Doesn't matter we get here parallel edges or not. It's not important. It's important that if this is chromatic, importantly, if this has chromatic index 4, one of these has chromatic 4. So suppose that this has chromatic 4, but both of them are chromatic 3. Yes, I will delete this here. Yes, so both has chromatic 3. I can without loss of generality, I can assume that color here is 1. I have 3 edge colorings, okay, and color here is 1, okay, because I can permute the colors. If here some other colors, I can permute to be 1. Change everywhere colors 1 and 2, 2 with 1, 1 with 2, okay. And now when I have this, I will go back and I will put here color 1, I will put here color 1. And then I get 3 edge coloring of this graph. And another way, if I have 3 edge coloring of this graph, can I 3 edge color this? 2 graphs? Let me a little bit clean the picture. So we are not making new photos, drawings, because we are not having that much time. So on this, no, I want to delete this one. Let's say we have two. Let's say we have. Let's say we have. Each time I erase something, this moves to drawing as mode, and I'm not using to update on this. On my iPad is differently settings. So let's say we have colored. Let's say we have colored this one with 3 colors. I claim I can color also these 2 graphs with 3 colors. So if we have 3 colored this graph, what will be the colors of these 2 edges? Same color by Blanusha. So you can choose which one. 1, 1. And then I put here 1, 1. And the other edges I get the same color. So if you have a big graph with 2 edge cut, which is chromatic index 4, then I know one of the 2 smaller ones will be of chromatics 4, at least one, maybe even both. So I then can say a reason why this has chromatic index 4 is because of this smaller one. So I reduce the reason to be chromatic index here 4 to this to be chromatic index 4. So then we say we don't like 2 edge cuts. We don't like multiple edges. We don't like loops because we don't have bridge. Bridge we can, okay. Can we say I don't like these 3 cycles in my graph? Can we reduce in the same fashion? can we reduce in the same fashion triangles? Are they reducible? Can we get rid of them? What are you going to do? That's exactly. Exactly. So I'm not going to write this claim. Maybe I can write it if you want. Maybe I can write it to be more clear. It is here. Not another proposition, yes. Let's make it proposition G cubic, 3 cycle, okay, let G prime obtain it from G by contracting x1, x2, x3 into a vertex x. Okay, we will draw it. Then so we have a triangle, we contract it to a vertex, we get another cubic graph. We don't care, we get parallel edges, I don't know, whatever, doesn't matter. We have smaller reason why it's not chromatic index 4. So we have something like this. Of course, we go first, we get rid of loops and bridges, then we go rid of 2 cycles, 2 cards, then 3 cycles, 3 cards, and so on. So let me draw it. So we have like this. Then we have this is our graph G, and let's say here is y1, y3, y4. Now we contract this into a vertex x. y3, no, this is 2. Sorry. This is the graph G prime. So we claim this is chromatic index 4 exactly when this is chromatic index 4. Oh, it's in this case it's easier, which is equivalent to say this has chromatic index 3 if and only if this has chromatic index 3. So let's go in this for such a claim. Let's go in this direction first. Let's say this one has chromatic. Let's say this one has chromatic 3, and we make it that key is 3. So if it has chromatic this one 3, at this vertex we're gonna have 3 different colors, 1, 2, 3, all of them. Yes. And when we go back to the bigger graph, we say, okay, we have here 1. We deduce here from this coloring color 3. So this comes here, this color comes here, and this color comes here. Okay. Now what should we put here to get 3 coloring? We have not much choices. We have to put. We will put here. We put here 2. We could put here 3, and we put here 1. this is in this direction. Okay? And how we prove in the other direction? We assume that we have here coloring, then we get coloring here. So let's say we have coloring here. We don't know that it looks like this. Okay. Now we go into this direction. We have coloring here, and we want to color here. So how this coloring looks here? We have 3H cut. Okay? 3H cut. What says Danusha? D3 colors, edges must be colored differently, yes? So we put color 1, color 2, color 3. Now when we contract, we get color 1, color 3, color 2. Perfect. So this way we prove this proposition. If G is cubic and we have 3 cycles, we can contract it, so and this holds here. So we don't like our snark to have 3 cycles. So after this, we do not like snarks to contain 3 cycles or triangles, yes. And there can be done a little bit more reductions, but we don't have time now to go each of them, yes. So somehow, okay, we come after a few more reductions, okay, we jump a few more, we come the snarks. Cyclically, I will explain the 4H connected cubic graphs of girth. You know what is girth? The shorter cycle of girth with chromatic four. This is some definitions with which most of the people will be happy. Someone even wants more. Someone even speak about cyclically 5H connected. I will explain what's mean cyclically 3H connected. We haven't defined it. So cyclically, I define it. Cyclically, G is cyclically, let's say G is cyclically KH connected. Just define general KH connected. It this cyclically if removing strictly less than k edges doesn't split G into 2 parts, both containing cycle. That's mean if I have situations like this, some edge cut, and on both sides I have some cycle, that's mean this number of edges must be at least k. Tell me what is cyclic edge connectivity of Petersen graph? Let's do it. You want to remove edges as small as possible on both sides to have a cycle. Actually, up to isomorphism, it's only a unique way how to do it, yes? So, one obvious way, and this is all the same, you have to remove this. Petersen graph is cyclically 5-edge connected. That's why some people prefer to go from 4 cyclic edge connectivity to 5. Yes, these people who do seriously research into Snarks. Yes. So for Snarks we remove it, bridges, loops, 2-edge cuts. You can remove 3-edge cut also. 4-edge cut you can remove in a way. Yes. 3 cycle, 4 cycle. There are reductions. Okay, we don't have time to do it. At the end, you will come. You are getting rid of everything what Petersen graph doesn't have it. And then at the end you will come Petersen graph. What do you think? Is the smallest snark. And you're gonna get today this exercise to prove it. So after these reductions, which we consider in several, there are even several more, which are more harder one. We consider the simplest one. But then we come to the conclusion that Snarks are cyclically 4-edge connected. Some people prefer 5 here. Cubic graphs are worth at least 5 with chromatic index 4. Yes. And smaller such graph is Petersen. Yes. So I didn't make it normal edge coloring. Yes. I knew I need 3 hours for edges. Yes. So maybe what do we propose? Afternoon we make some more normal edge coloring and then exercise. Yes. And then tomorrow, or we do exercise now, but tomorrow we have normal edge colorings and two. So okay, let's see. I decided I will prepare exercise for today and update how I'm successful with coloring exercise. If I'm not, I will teach normal edge coloring. If I'm yes, we will leave normal edge coloring for tomorrow a little bit. Yes, we can do like that. Okay, so we stop for now.